The world you see seems solid. A chair is a chair. A rock is a rock. If you close your eyes and open them again, the chair is still there. It didn't spend the time you weren't looking being a fuzzy cloud of potential chairs. It just stayed a chair. This seems obvious. It's the foundation of our entire experience of reality. But the strange thing is, the fundamental theory that describes all the stuff that makes up that chair and that rock says something very different. That theory is quantum mechanics, and at its very heart is a deep, frustrating, and fascinating contradiction. It's called the measurement problem. To understand the problem, you first have to understand the weird rules of the quantum world. The world of tiny things. Electrons, photons, the building blocks of everything. According to quantum mechanics, these tiny things don't behave like the big things we're used to. They don't have definite properties until you look at them. Imagine an electron. An electron has a property called spin. For our purposes, you can just think of it like a tiny spinning top. It can be spin up or spin down. Now, in our everyday world, a spinning top is either spinning clockwise or counterclockwise. It has a definite state, but an electron, when you're not looking at it, is not spin up or spin down. It's in a state called a superposition. It's a weird, ghostly mix of both possibilities at the same time. It has a certain probability of being found as spin up and a certain probability of being found as spin down. This isn't just a statement about our ignorance. It's not that the electron is one or the other, and we just don't know which. The theory says it is, in a very real sense, both at once. It's a wave of possibility, not a solid little particle with a fixed property. This wave of possibility is described by a beautiful and powerful piece of mathematics called the wave function. The wave function is like the ultimate recipe for a quantum particle. It contains all the information about it. It tells you the probability of finding the electron here or there, or with this spin, or that spin. And there's a famous equation, the Schrödinger equation, that describes how this wave function changes over time. And here is the first critical piece of the puzzle. The Schrödinger equation is completely deterministic. It's smooth, it's predictable. If you know the wave function now, you can use the equation to calculate exactly what the wave function will be at any point in the future. It just evolves, smoothly and continuously, like a ripple expanding on a pond. The superposition just keeps on superposing. The cloud of possibilities just keeps on being a cloud. This is rule number 1 of quantum mechanics. It's the rule for how things work when no one is watching. But then we decide to look. We want to know, is the electron spin up or spin down? So we build a machine to measure it. We interact with it, and the moment we do, something dramatic and completely different happens. The superposition vanishes. The wave function collapses. Instantly, the electron is forced to choose a state. It becomes either spin up or spin down. The wave of many possibilities suddenly and randomly snaps into one single, definite reality. The ghostly mixture is gone. Now we have a solid fact. The measurement reads spin up. If we did the same experiment again with an identical electron, it might read spin down. The outcome is fundamentally random. The wave function gives us the odds, but it can't tell us what the specific outcome will be. This is rule number 2. It's the rule for what happens when you make a measurement. And right there, that's the measurement problem. We have 2 completely different sets of rules for how reality works. We have the smooth, predictable, deterministic evolution of the wave function, rule 1. And we have the sudden, random, unpredictable collapse of that wave function during measurement, rule 2. The problem is that the theory doesn't tell us what counts as a measurement. What is the magic ingredient that makes rule 1 stop and rule 2 take over? Is it a conscious observer? A human with a PhD in a lab coat? That seems incredibly arrogant. Does the universe care if the thing looking is a person? What about an automatic non-conscious detector, like a Geiger counter? A radioactive atom is in a superposition of decayed and not decayed. The Geiger counter is a big thing made of atoms. When does the collapse happen? When the radioactive atom interacts with the first atom in the detector. Or when the signal travels up the wire, or when it makes a clicking sound, or when a computer records the click, or when a person reads the computer screen. The theory draws a completely arbitrary line between the quantum system being observed and the classical device doing the observing. But the classical device, the Geiger counter, is just made of quantum particles. It's just a giant collection of atoms, each one governed by the Schrödinger equation. So why shouldn't the whole system, the radioactive atom and the Geiger counter, just evolve together smoothly according to rule 1? The whole combined system should just enter a bigger, more complicated superposition. This is where the famous Schrödinger's cat thought experiment comes in. It was designed by Erwin Schrödinger to show how absurd this whole situation is. Imagine you put a cat in a sealed box. Inside the box with the cat, you place a vial of poison gas. The vial is hooked up to a hammer, which is controlled by a Geiger counter. The Geiger counter is aimed at a single radioactive atom. This atom is governed by quantum rules. Over the course of 1 hour, there's a 50% chance it will decay and a 50% chance it won't. If the atom decays, the Geiger counter clicks. The click releases the hammer. The hammer smashes the vial. The gas is released. The cat dies. If the atom does not decay, none of this happens. The cat lives. Now, according to Rule 1 of quantum mechanics, after 1 hour, the atom, since it hasn't been observed, is not decayed or undecayed. It's in a superposition of both states. But because the entire system is linked, this means the Geiger counter is in a superposition of clicked and not clicked. The hammer is in a superposition of fallen and not fallen. The vial is in a superposition of broken and not broken. And the poor cat, therefore, must be in a superposition of dead and alive. This is not a metaphor. According to the strict application of Rule 1, the cat is literally both dead and alive at the same time, described by a single complex wave function. This is obviously insane. We never see half-dead, half-alive cats. Cats are either one or the other. Then you open the box to check on the cat. You make a measurement. At that moment, the entire wave function collapses. You instantly find either a living cat or a dead cat. So the measurement problem is this. What exactly causes the collapse? When does nature stop following the smooth, elegant Schrödinger equation and suddenly jump to a random, definite outcome? What is the dividing line between the quantum world of superposition and the classical world of definite things? The theory of quantum mechanics, for all its incredible success, doesn't say. It just puts a black box around the word measurement and doesn't explain what happens inside. This isn't just a philosophical nitpick, it's a gaping hole in our most fundamental description of reality. Physicists have been arguing about it for nearly a century, and they've come up with several possible ways to think about it. These are not different theories, but different interpretations of what the same mathematics actually means. The oldest and most traditional one is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, the pioneers of quantum theory. Their answer to the problem was, in essence, to say it's not a problem. They argued that there is a fundamental dividing line between the quantum world and the classical world of our measuring instruments. Quantum mechanics describes the fuzzy world of possibilities. Our lab equipment and our own experiences exist in a separate classical world of facts. A measurement is what happens when a quantum system interacts with a classical device. In this view, it's meaningless to ask what state the electron was in before you measured it. It didn't have a state. It's also meaningless to ask what the cat's state is before you open the box. The whole concept of a dead and alive cat is a misapplication of quantum theory to a large classical object. The theory is about predicting the results of experiments, and that's it. This is often summed up by the phrase, shut up and calculate. It works. It gives the right answers for all practical purposes, but for many, it's deeply unsatisfying. It avoids the question by declaring it off limits. It doesn't explain why there's a dividing line or where it is. It just says there is one. This dissatisfaction led to other, more radical ideas. One of the most famous is the many worlds interpretation proposed by Hugh Everett III. Everett looked at the two rules and made a bold suggestion. What if we just get rid of Rule 2? What if the wave function never collapses? In this view, the Schrödinger equation is the whole story. The wave function always evolves smoothly and deterministically, so what happens when you measure the electron's spin? The superposition doesn't collapse. Instead, the entire universe, including you, the observer, gets pulled into the superposition. The universe splits. In one branch of reality, the electron is spin up, and a version of you sees it as spin up. In another, completely separate branch of reality, the electron is spin down, and a different version of you sees it as spin down. Every single quantum measurement, happening trillions of times a second, all over the universe, is constantly splitting the universe into a near infinite number of parallel worlds. This sounds like science fiction, but it's a very serious proposal. It elegantly solves the measurement problem by erasing it. There's only one rule, Rule 1. The cat in the box really is both dead and alive. But the dead cat state is part of one universe, and the alive cat state is part of another. When you open the box, you just find out which branch of the universe you happen to be on. The main weirdness here is, of course, the staggering idea of countless parallel universes that we can never interact with. It also has trouble explaining the probabilistic nature of quantum mechanics. If both outcomes happen, why does it feel like there's a 50-50 chance? This is an ongoing area of debate within the many worlds framework. A completely different approach is to suggest that quantum mechanics is incomplete. These are called hidden variables theories. The most famous is the de Broglie-Bohm theory, also known as pilot wave theory. This idea says that the wave function isn't the whole story. Superposition is not a description of the particle itself. Instead, particles like electrons are always real particles. They always have a definite position. They are never in two places at once. So what is the wave function? In this theory, the wave function is a real physical thing, a pilot wave that guides the particle around. The particle is like a surfer, and the wave function is the wave telling it where to go. The wave itself evolves according to the Schrödinger equation, and the particle is pushed along by it. This view solves the measurement problem completely. There is no collapse. A measurement isn't some special process. It's just a normal physical interaction where we happen to find out where the particle, guided by its pilot wave, actually is. The randomness of quantum mechanics is just an illusion based on our ignorance. We don't know the particle's precise starting position, so we can only predict its final position probabilistically, even though its path is completely determined. Schrödinger's cat is never both dead and alive. The radioactive atom either decays, or it doesn't, based on the definite but unknown position of its internal particles. The outcome is fixed from the beginning, we just don't know what it is until the end. The main issue with this theory is that the pilot wave has to be non-local, meaning it can influence things instantaneously across vast distances, something Albert Einstein famously disliked, calling it spooky action at a distance. Then there are theories that take another route. Instead of getting rid of collapse like many worlds or explaining it away like pilot wave, these theories try to make collapse a real physical process. These are called objective collapse theories. They suggest that the Schrödinger equation is not perfectly correct. It's only an approximation. These theories add new mathematical terms to the equation. These new terms cause the wave function to spontaneously collapse on its own, without any need for a measurement or an observer. This collapse is a random physical event. For a single particle, the chance of this happening is incredibly small. An isolated electron might exist in a superposition for millions of years before collapsing. But here's the clever part. The probability of collapse is multiplied by the number of particles in the system. For a large object like a Geiger counter or a cat, which are made of trillions upon trillions of particles, the chance of collapse becomes enormous. The superposition is destroyed almost instantaneously, far too quickly for a state like AD and a live cat to ever form. This approach is very appealing because it provides a physical mechanism for collapse. It explains why we see quantum weirdness in the micro world but not in our macro world. The line between quantum and classical is no longer arbitrary, it's a matter of size and complexity. The bigger something is, the faster it is forced to have a definite state. The best part about these theories is that they are, in principle, testable. If collapse is a real physical process, it should have subtle side effects, like producing a tiny amount of heat. Experiments are underway to look for evidence of spontaneous collapse, but so far none has been found. A more recent and mind-bending interpretation is called QBism, or quantum Bayesianism. This one takes a radical turn by suggesting the problem isn't in reality, but in our description of it. QBism claims that the wave function is not a real physical thing out there in the world. It doesn't describe the electron, it describes our knowledge of the electron. The wave function is just a mathematical tool that an agent, an observer, like a scientist, uses to make the best possible predictions about the outcomes of future measurements based on their past experiences. It's a statement of belief of subjective information. In this view, wave function collapse is not a physical process at all. It's just you updating your knowledge. Before you measure the electron's spin, there's a 50% chance of up and 50% chance of down, so that's what your wave function reflects. Then you do the measurement and you see spin up. You now know the result with 100% certainty. So, you update your knowledge, your personal wave function, to reflect that. The collapse happens in your mind, not in the world. This dissolves the measurement problem because the spooky dead and alive cat was never a physical reality. It was just a reflection of your 50-50 uncertainty about the cat's state. Once you open the box and get new information, you update your beliefs. The main criticism of QBism is that it feels anti-realist to many physicists. It seems to make science about the observer's subjective beliefs rather than about an objective external world that exists independently of us. So, Where does this leave us? We have a theory, quantum mechanics, that is arguably the most successful scientific theory in human history. Its predictions have been verified to an astonishing degree of accuracy. It's the foundation for our understanding of chemistry, materials science, and all of modern electronics, computers, lasers, smartphones. Yet, at its very core, it has this deep, unresolved puzzle about how reality works. It matters because the question goes to the heart of what we consider to be real. What is a thing? Does a rock have definite properties when no one is looking at it? Copenhagen says the question is meaningless. Many World says yes, but there are infinite other rocks with other properties in other universes. Pilot wave theory says yes, its properties were always definite. Objective collapse says it's forced to be definite by a physical process. QBism says the properties are a feature of our interaction with the rock, not the rock itself. These are not small differences of opinion, they are wildly different pictures of the universe. For most of the past century, the shut up and calculate approach has dominated. As long as the math worked, most physicists were happy not to worry about the philosophical baggage. But that might be changing. As we push the boundaries of technology, building quantum computers that try to harness the power of superposition on a larger scale, these questions might become more than just philosophical. Understanding the true nature of measurement could be key to overcoming the technical hurdles of building these powerful new machines. Ultimately, the measurement problem is a profound reminder of our own limitations. We have found a set of mathematical rules that perfectly predict the behavior of the universe at its most fundamental level. But we don't seem to have a clear and coherent story to tell ourselves about what those rules mean. The world we see every day, the world of solid chairs and definite cats, emerges from this bizarre probabilistic quantum foam. The process by which the fuzzy potential of the quantum world hardens into the concrete reality of our experience, that process, the act of measurement, remains one of the greatest unsolved mysteries in all of science. It's the gap between what the world is and what we see, and we are still staring into it, wondering what it means.